the Milky Way after Gaia, top 7 new facts about the structure of our galaxy from the last 5 years. Not long ago, the Milky Way presented in textbooks looked rather orderly, a spiral galaxy with a thin disk, several spiral arms, a central bar, and more or less smooth dynamics. But with the release of data from the Gaia mission, that picture began to collapse rapidly. Instead of a quiet system, we are gradually seeing a far more complex and non-equilibrium structure shaped simultaneously by waves, asymmetries, traces of ancient collisions, and processes of internal restructuring. The modern galaxy is not a static object, but a dynamic system still ringing and vibrating after past disturbances and interactions. Fact 1. The solar neighborhood, from the Gould Belt to the Radcliffe Wave. One of the most dramatic revisions concerns our immediate cosmic neighborhood. For more than a century, astronomers believed the Sun was surrounded by an inclined ring of young stars known as the Gould Belt. However, recent studies suggest that this is not a real physical structure, but rather a combination of several independent stellar populations and observational biases. The key breakthrough came with the discovery of a different structure, the Radcliffe Wave, identified in 2020, a gigantic wave-like chain of gas and young stars stretching about 2.7 kpc through regions such as Orion and Perseus. Further studies reveal that this structure is not static. It oscillates relative to the galactic plane and slowly drifts radially through the disk. Moreover, a significant fraction of nearby young stellar clusters appears to be connected to only a few major star-forming complexes. As a result, the belt dissolves into an illusion, while the real structure emerges as a wave propagating through the local interstellar medium. Fact 2. The disk is not in equilibrium, spirals in phase space. Gaia data revealed that even the local galactic disk is far from dynamical equilibrium. One of the key discoveries was the so-called phase spiral, a spiral-shaped structure in coordinate velocity space (z/vz), reflecting vertical oscillations of stars. This feature is interpreted as evidence of a relatively recent perturbation, likely caused by the passage of a dwarf galaxy such as Sagittarius. Importantly, this structure is not confined to the solar neighborhood. Its shape changes with galactic radius and depends on the age and chemical composition of stars. This means the disk remembers past dynamical events, and these signatures can be used to reconstruct the Milky Way's history. Fact 3. The warp of the galaxy and vertical waves. Another major result is the re-evaluation of the galactic warp and vertical waves. Previously, the warp was treated as a relatively simple bending of the outer disk. It is now clear that this is only part of a much more complicated picture. The Milky Way disk undergoes large-scale vertical oscillations. Recent work suggests that beyond the Radcliffe Wave there may also exist an even larger structure, the so-called Great Wave, observed on much larger scales. These waves are likely connected to interactions with dwarf galaxies and to asymmetries in the galactic dark matter halo. Fact 4. Spiral arms, geometry becomes physics. The classical picture of spiral arms has also changed. Thanks to Gaia data and observations of Cepheids, young stars, and chemical traces, astronomers can now map the galaxy's spiral structure using several independent methods. These studies show that the arms are not perfectly symmetric. Different arms vary in density, age, and possibly even lifetime. Moreover, spiral structure manifests itself not only spatially, but chemically as well, for example, in metallicity distributions. This means the arms are not merely a visual pattern, but dynamically important components of disk evolution. Fact 5. Stellar streams, a gravitational scanner of the galaxy. One of the most powerful tools of modern galactic astronomy has become stellar streams, elongated structures formed through the tidal disruption of clusters and dwarf galaxies. While they were once regarded mainly as relics of the past, they are now used to measure the current gravitational potential of the Milky Way. Analysis of streams in Gaia DR3 data has refined estimates of the galaxy's mass distribution, including the shape of the dark matter halo. Stellar streams are highly sensitive to irregularities in the gravitational field, allowing astronomers to detect substructures and even trace the influence of the Large Magellanic Cloud. Fact 6. The bar and radial migration, redistribution of stars. The central bar of the Milky Way turned out to be far more than a simple morphological feature. It is now understood as a key dynamical engine of the galaxy. Recent studies show that the formation of the bar was accompanied by episodes of radial migration, during which stars moved significant distances across the disk. This process mixes stars of different ages and chemical compositions, producing the gradients we observe today. In other words, the bar directly shapes the structure of the entire galactic disk, not just the central region. Fact 7. Even the rotation curve is not the final answer. Even such fundamental properties as the galactic rotation curve remain under revision. New estimates based on Gaia DR3 suggest possible deviations from the classical flat rotation curve, which directly affects estimates of the mass and distribution of the dark matter halo. However, different methods still produce somewhat inconsistent results, and one of the main challenges now is understanding systematic uncertainties and the limitations of current models. Main conclusion: the Milky Way is a non-equilibrium system. If all these discoveries can be summarized in a single statement, it would be this. The Milky Way is not a static spiral galaxy, but a non-equilibrium dynamical system shaped simultaneously by density waves and vertical oscillations, traces of past mergers, radial migration of stars, local star formation structures, and the influence of dark matter and satellite galaxies. Structures such as the Gould Belt disappear under more precise observations, giving way to physically grounded features like the Radcliffe Wave. For the first time, we are beginning to see not merely a picture of the galaxy, but its dynamics unfolding through time. What comes next? The coming years will likely focus on combining these discoveries into a unified galactic model. Future Gaia data releases, radio and infrared observations, and increasingly sophisticated simulations will help connect local structures, global dynamics, and the Milky Way's formation history. And perhaps the most important shift has already happened. We have stopped seeing the Milky Way as geometry and begun to understand it as a process.